And you? Okay. Alongside. Tomorrow, yeah. Today, tomorrow, and then tomorrow. Sure. How long have you been here? Only Friday. You were here for how long time? Since the beginning of last night. 2 weeks. Did you arrive yesterday? How long will you stay? 3 weeks.
So my name is Navier-Stokes. I have just arrived to Cambridge and I'm happy to share this session. And the first speaker is going to be Ning Jiang from Wuhan University and will learn something on the Ericksen-Leslie model.
Yes, thank you. Thanks, organizers, inviting me to here to give a talk. And unfortunately, my inviter Zarnescu is not here this week. Okay, so my talk is about my recent work with my collaborators on the inertial Ericksen-Leslie model for the pneumatic liquid crystal and its zero inertial density limits. So in the advertisement of this talk, I called it hyperbolic Ericksen-Leslie, but now I change it into this name because I think hyperbolic Ericksen-Leslie. I mean, this name is not well accepted. Okay, so anyways, including the inertial effect. So this is a collaborator. So has it's a serious work, and but the major one is my student in Wuhan, and also some my postdoc Tang at the USTC and other, and include one of the work is collaborate with Zarnescu. Okay, so we started from it's well known that Ericksen-Leslie system for liquid crystal started in the 660. First by Ericksen, and then modified it by and developed by Leslie. So here we take the form. We take the form from the classical paper of Leslie, some constitutive equations for liquid crystals on archive 1968. So here the system includes the balance of the momentum here and the balance of angular momentum. So I just use the same notation as Leslie in Leslie's paper. So and here the unknown functions are u. U is a bulk flow velocity. The d is a direction field of the liquid molecules and with length 1. Okay, just to point to the direction. And here is for simplicity, we put this rho, the fluid density, as constant. Okay, but the non-constant fluid model does exist. Okay, in fact, in Leslie's paper. Okay, so I will take briefly later. Here, the rho 1, this non-negative constant. Rho 1 is so-called inertial density. Okay, so here G hat is intrinsic force associated with D, and pi is a direct stress, and F and G are external body force and external direct body force. So here and A, we introduce some notations. A is the rate of a strain tensor. B is antisymmetrical part of the skew symmetric part of the strain tensor. So this omega, this D dot is first material derivative of D. This N is a rigid rotation part of the director, changing rate by fluid vorticity. Sometimes it's called odoroid derivatives. It's Zarnescu taught me. He said this guy is called this derivative. Okay, and the constitutive relation here, rho or sigma hat, pi g hat are given by this. Yeah, this here g hat, here p pressure sigma, and the w is cosine Frank energy. Yeah, you will see it just in the next page. P is the pressure, and here beta, and the scalar function gamma is Lagrangian multipliers for the geometric constraint. The length of D is 1. Here the okay, so W is Olsen-Frank energy functional, like this form. Okay, it's well known in liquid crystal. Here G is kinematic transport. Has 2 parts. The first part, its first term is the rigid rotation of the molecule. The second term represents the stretching of the molecule by flow. Here sigma is a stress tensor include 6 parts, the mu1 to mu6. These coefficients are usually called the Leslie's coefficient, and among them, the mu4 is the usual viscosity. So I write the divergence sigma as 2 parts. This is the viscosity part with Laplace, and another one is theta. And here is a relation. The number 1 is mu2 minus mu3. Number 2 will be mu5 minus mu6. Here is a mu1. The sign of a mu number 1 is always usually non-positive. So it's strictly negative or equal to 1 will play a significant role in our analysis. Here is a so-called Veronese relation. Here, it's also play a role in analysis. So just for simplicity, assume here rho equal to density is 1, and external force is 0. And we also take the K1, K2, K3 equal to 1, and K4 equal to 0. This is just because the difficulty from the analysis. So currently we can only treat this kind of this. Okay, so originally the derivation of the dynamical equation was proposed by Erickson, then adjusted by Leslie. Start from the form of energy balance. Here's I emphasize here the part. Here's the inertial part. So here's this is dissipation, and W is Olsen-Frank energy. So the question is usually in the past decades. So people only usually investigate the model which just delete this rho 1. Okay, so people usually don't consider this inertial effect. And so the question is, okay, why do we investigate this? Okay, now I found some source. Okay, concerning the internal constant rho 1. Frank and Leslie in 1978, he stated in this paper, he said his original words as the term involving sigma. Here his sigma is just notation, different notations. His sigma is here one. The term involving sigma represents the rotational kinetic energy of the material elements, and therefore sigma is an inertial constant, while this contribution to the kinematic energy is undoubtedly negligible in most circumstances, but we return it in the general form in which follows, since it could be conceivably play a non-trivial role when the anisotropic axis is subject to large acceleration. Okay, in summary, this inertial effect sometimes, it does play a role. And we will say mathematically this term is very interesting. Here, so we can write this Ericksen-Leslie's inertial liquid crystal model reduced to the following form. Okay, the first system, here the left-hand side is a standard Navier-Stokes. Here we can consider this as a force, a divergence free. And here the part is the d double dot is a second material derivative. So that's why sometimes we call it hyperbolic. And with because of the constraint, the d length is 1. So the Lagrangian, we can calculate the Lagrangian multiplier gamma has this form. And because it's a wave equations, yeah, because the third one, the D, so we need initial data, two initial data. So here's U and the D has the two initial D and the D dot, okay? So here, and because of its length 1, so there is initial data has some constraints for some compatibility condition. Now, even it's a very special form. I mean, the special form is what? We just suppose this term, this stress term just vanish. That means mu1 to mu6, except mu4 just vanish. So this case, of course, this because of the relation we mentioned before. So here's a lambda 1, lambda equal to 2. So the system reduced to this one. And you look at this. This is nothing but a nonlinear coupling of a standard incompressible Navier-Stokes and the wave map with target manifold S2. So here, so the special case, if mu equal to 0, if D is just constant vector, so the U satisfies the standard incompressible Navier-Stokes. And if U equal to 0, so note here, if U equal to 0, the first system is not vanish. Okay, so you put this guy is that means grid P equal to this guy, and this has a specific name. Okay, so Ericksen, in a very short paper, 1968, he called this the solution of this part with the U equal to 0. It's called the twisted waves. Okay, yeah. So now before. So usually people now consider that if this initial constant rho 1 is 0, and mu1 just take a negative 1. Okay, for simplicity, just negative 1. So the system reduced to the parabolic Ericksen-Leslie system. So in the literature is just the Ericksen-Leslie system. So it's a mathematical study. Was initialized by Bob Harden, David Kindlesser, and Huang in middle 80s, and so it's a static analog of the parabolic Ericksen-Leslie is just Olsen-Frank model. So they start from the calculus variation point of view to study the existence, the regularities or partial regularities, and something like that. And after 10 years, Chun Liu, a student, PhD student with Huang, in his thesis, they consider the so-called Gendtman-Landau approximation of the parabolic Ericksen-Leslie. So they derive the partial regularity and the regularity. Here's the Gendtman-Landau approximation is to approximate because of the serious analytical difficulty brought by the geometry constraint D length of D equal to 1. So they consider a so-called Gendtman-Landau approximation is just replace that term by D squared minus 1 squared over epsilon. So now they even for that case they derive the global existence, global solution, and its partial regularity. Okay. So by the way, so let me remark that started from this the work and Huang eventually give a simplified proof of Caproni-Kohnenberg on the partial regularity of incompressible Navier-Stokes later. So now, and after another 10 years or maybe even 20 years, so now they go back to the original model. I mean, without a Gendtman-Landau approximation. Huang, Wang, his postdoc, another student, Eugene, and later on, a couple of years ago, with Wang, they prove a global weak solution with some assumption, which avoid the possible singularity, finite time singularity of the heat flow. Okay, so anyway, it's even for the parabolic Ericksen-Leslie system, still some very challenging analytical work left. So and of course for more general parabolic system, so many people did work on this. So now there is a story. So I encountered, I visited the Koran Institute 3 years ago, and I encountered Huang. Yeah. I was postdoc at the Koran 10 years ago. So I chatted with Huang, said, okay, so crystal is so interesting. So can I do something with you? Can you suggest some problems? And Huang said, okay, so for parabolic Ericksen-Leslie, I have been working on this field 30 years. Okay, so what's left is only just very hard problem. So, but you can do something else. For the hyperbolic case, it's almost empty. Okay, so that's he mentioned this here is if we do keep the inertial part, is rho 1 positive. So very analytic work for the general model, except for very special case. I mean, just completely forget about the U, or only consider under 1D, one dimension. Even for this simplest case, it's very subtle. So there are some work, and there's Sexton on here, this time the 1989, because the singularity of the variational wave equation, and later on Bob Glassy, John Hunter, and Yu Shizhen, and Chun Liu and his younger collaborator did some work, and there's some work as Ali Bai and John Hunter, so they did some basically formal analysis without rigorous analysis to some rotational waves. Here's a twistor wave. And Yu Shizhen and Pin Zhang, and later on the Brisson, they consider a more general, yes, as I said, for this special case, the hyperbolic, the inertial Ericksen-Leslie system belongs to a so-called, has a structural variational wave equation. So they work on this for more than 10 years. Okay, so for general model, I mean, general model is keep U here and the higher dimension. So a parent, an obvious difficulty coming from the double material derivative on B, which is a nonlinear operator on the D. The D double dot is like this form. Okay, so it looks horrible. And the most troublesome part is Lagrange multiplier gamma that generates a higher derivative. In particular, if you add the unit length constraint, the situation gets even worse. So that's so even I mean, Huang suggests to me, okay, might work on this this problem, but I didn't work it out. However, at September 2016, one of our organizers of this program, Zarnescu, and his collaborator Diana, they posted 2 papers, but not on Ericksen-Leslie system inertial, but on a Q tensor model. Q tensor model analog. They work on the so-called tensor model, proposed in 1998. So this is a tensor. But okay, today I will not go in details about this tensor model. It's a Q tensor model. But I want to emphasize is here in their model, they did consider they kept this initial part. This J is a positive. And they tried to prove the global existence, something like this. Okay, here what they did, they proved the global existence and the uniqueness for the small initial data with some assumptions. First is they assume the Newtonian viscosity is a beta 4 is large enough. Another one, the key assumption is a coefficient A positive, which gives the so-called damping. Yeah, they call it their technical trick is a higher order commutator estimate. Okay, from my point of view, okay, it's just some subtle energy estimate, and they tried to find the global in time twisted wave. Okay, as proposed by Erickson. That means that's a solution of the coupled system for which the flow and U just zero. Unfortunately, the class of twisted waves they found are not very physical. Okay, so it's still very hard one. And later on, they consider the inviscid case. So together with Edward Fraser and Roca, and this one they employ the concept of pure Louis on the incompressible Euler. They prove the existence for the dissipative solution. Okay, this is the first, to my point of view, to my knowledge, so it's the first results involving the second order material derivative. Okay, so many open questions left in this direction. Okay, so Zarnescu's work on this Chance model did give me some confidence. Okay, so if they can treat the Chance model with this second order derivative, I will try the harder one. I mean, this inertial Ericksen-Leslie. Okay, that's my work. Now, by the way, I remark that there is also the corresponding compressible model. In fact, this is proposed in the Leslie's paper I mentioned before. Okay, so that's our result. So now, because of the limit of time today, so I will focus on just two of them. So my work on in this field includes two parts. The first part is just well-posed, is of in the framework of a classical solution, a smooth solution. So the incompressible model and the compressible model. But let's focus on incompressible. Incompressible model has two results. First one is lambda 1 is less than 0, similar to the Q tensor model. So this gives us some extra damping. So this is our first paper is just published on Science Mathematical Analysis. So and the lambda 1 equal to 0 is much harder. So we did the similar result last year. Okay, so also did something for compressible model, but for lambda 1 equal to 0 for compressible model is still open because of a lack of enough decay on the velocity. Now, so the so-called zero inertial limit is what? Is let the inertial constant rho 1 go to 0. We want to justify formally, so it's the inertial hyperbolic and Ericksen-Leslie system will converge to the parabolic Ericksen-Leslie system. So for very special case, as for the special case, I mean, let u equal to 0. So for this case, and we and Tang, Lo and Tang and Zarnescu, we proved this. And recently, very recently, I and my student Lo, and we justified for general case, but for lambda 1 equal to less than 0. So general principle. So first, so lambda 1 less than 0 case is relatively easier because this negativity gives some damping effect. So lambda 1 equal to 0 case is essentially related to the wave map type equation. So with target manifold S2. So all about this work, we need some natural constraint, restriction on the coefficient, I mean nesting coefficient. So let's start from here. So for the well-posedness, so now we have a basic.
Can I interrupt just a second? And I don't know if this problem is shared by other people. I've forgotten now, after all this, what is the equation you are now addressing?
Okay, we are addressing. This one. This one is lambda 1 less than, okay, for this one, for two cases, lambda 1 less than 0 and the lambda 1 equal to 0. This is the equation we are addressing.
Okay, but you did, at some point you started talking about sigma tilde, and I think you even set that to 0 at some stage.
Oh, that's a very special case.
Yeah, you're not talking about that now?
No.
Okay.
Yeah.
So, but in general, sigma tilde and lambda 1 depend on each other.
Yeah.
So the lambda 1 actually is inside sigma tilde.
Yeah, they are related because you see, lambda 1 here is also, lambda 1 here has a relation with mu2 and mu3. mu2 and mu3 is part of it in this yes. Sigma tilde.
Okay. So arbitrarily removing sigma tilde is not really allowed.
No.
Okay.
Yeah.
But now you're talking about the, okay,
yeah,
so
yeah,
that's fine.
Yeah. Okay, so lambda tilde, yeah. Okay, I should say it this way. The key part is this lambda 1 is 0 or not 0. If this lambda 1 is a negative, strictly negative, so even sigma tilde is there, not vanish, it's relatively easier than the case that lambda 1 equal to 0 without epsilon tilde.
Okay.
Clear? Yeah, so here the lambda 1 is less than 0 or equal to 0 is a key point. Because in the third equation, this lambda 1 less than 0. So from mathematically, I mean from point of view of analysis, it will give us some damping effect. But if lambda 1 equal to 0, so this is purely a hyperbolic, dispersive type equation, wave map with a target S1, S2. That's give us a tremendous difficulty.
Okay.
But fortunately, we did some work on this direction. Okay, so yeah, maybe I missed too many model here and give you some confusion. Okay, let's first now this let's go back to this equation. If there is a smooth solution with lambda 1 equal to 0 or non-zero, okay, so we have a basic energy dissipation law. But this is not new, because this is basically derived by Ericksen-Leslie, but we just use our language. And so to make this energy law dissipative, so we need some satisfy some condition. So I checked the original paper of Leslie, the mentioned in the first page. So this is nothing but coming from entropy equality. Okay, so it's not new. I didn't claim it's new.
Can I make a remark here? Leslie's inequalities are not exactly like this.
Not exactly like this.
Actually, mu1 is always strictly negative. There is no liquid crystal that has mu1 positive. So it could be, as big as minus 2,000 units to minus 5,000 to minus 100. So, and the problem is that the term with mu1 scales in a very different way than the other terms. But this is essential in liquid crystal flow.
Yes, I agree.
Yeah.
Yeah. Thank you. Yeah. Now I talk about some mathematics. Okay, so you say our one here a constraint, the length of d equal to 1. So to do a PDE, okay, we should, what's a standard strategy of PDE? Okay, we construct a approximate solutions and convergence, and so that the limit is satisfied by this equation. But with this constraint d equal to 1, so if d we modify this d, so it's harder to still keep it as with the unit 1. So to remove this problem, so what we need for why is for the parabolic case is not a problem, because for parabolic system we have a maximum principle, so we only require initially at t equal to 1, t equal to 0 initially, so it's a unit 1 at a later time they will prove it's a keep the 1. So so the system itself we don't need to put this constraint. So now what we need here is to say that if U is smooth enough, we can also prove that when gamma has this Lagrangian multiplier like this form, and they initially satisfy this constraint, then at a later time the norm also equal 1. Okay, so we introduce a new variable h equal to d squared minus 1 and solve this system with a given smooth vector field, and we can prove that at a later time this h is also 0. So that give us so that means we do not need the norm of this u during this approximation process is 1. So we need only to put this constraint initially. So later on, so we can solve that given this u and the d satisfy this hyperbolic equation, we can prove its existence. Then we carefully construct here this is our main result. So for smooth enough initial data and initial energy, okay, so if Leslie coefficient satisfies the relation such that this basic energy is dissipative, so no matter lambda 1 equal to 0 or equal to 0, so if the initial energy is finite, so there exists a time which is finite depending only on the initial data, such that the inertial Ericksen-Leslie system has a solution and it has energy law like this. Okay, this is our first result. The second result is if number 1 less than 0. So so the initial data, if initial data is small enough, we can prove a global in-time solution and with this energy law. So that means this result says that, okay, so no matter number 1 equal to 0 or less than 0, so we have a local in-time existence for the small solution. But when number 1 less than 0, so we can show that if initial data, initial energy is very small enough, we can prove a global in-time solution and with this energy law. So now here, so I just show you one page here. So we carefully design this iteration approximate system. So first this one is we design it as a Stokes type. And here, so this type with given u, we can solve d as the previous lemma indicates, and and finally we can design this energy and we can prove this energy law. Okay, so this is one, and we for each time, so we have a local existence, but we have to prove for each case this time interval has a uniform lower bound. Okay, so finally, okay, so we skip here. This for some very delicate norm design. Okay, now number 1 equal to 0 case, there is no damping. So the original inertial Ericksen-Leslie system reduced to this form. Now look at here. The first equation is still here, and then now sigma. Now I can answer your question. So for here, for the very general sigma tilde, we have some difficulties. Note there we have a mu1 to mu6, right? But for some mu3 or mu4 is mu5 or mu6 is non-zero, so we couldn't treat so far. Have some difficulty, but we can treat this case. This little bit easier case. I mean, this lambda is here mu1 and mu2 and mu3 and mu2 and mu3 equal. For this case, the lambda 1, because of the relation lambda 1 equal to mu2 minus mu3. So here when mu2 equal to mu3, so lambda 1 is 0. Here now for this case, now for an even more special case, that means this divergence sigma is totally vanished. Another two guys, Chai and Huang, they treated this special case. For this case, now for this case, note this D is really a wave map equation, a wave map type equation. So for this case, we employ some technical from geometric dispersive equations. So we employ the method of a so-called vector field method, which is from the geometric dispersive equation. So the key is what is we find some vector field. Here's a angular vector field, and here S is and it's tau is dt d1 and omega is, and this vector field is invariant under the scaling. So and we rewrite the equation by this new vector field. I mean new coordinate system, and we can rewrite the system and to use the technique from the wave map. We can prove the following one. The equation here, our result is with Huang and Zhao from USTC. So under constraint, this mu, okay, and the initial data near a equilibrium, which is u is 0, and another one is near a constant vector, satisfies the Sporsley's assumption here, and there is a unit global solution satisfying the initial data. Okay, this is we can, the key is we can justify, we prove this uniform estimate. Here we must employ the time decay of the incompressible Navier-Stokes. Note here we proved for 3D, three-dimensional spatial dimension. For 2D case it will be much harder. Why? Because from the technical point of view, so for you know, for wave equations, dimension is lower, the difficulty is harder. Okay, so for two-dimensional case, the decay of a compressible Navier-Stokes is not enough to close this energy estimate. So now let's go to the second part, which I will focus on. Here's a zero inertial density limit from hyperbolic to parabolic Ericksen-Leslie. So formally, so inertial constant ρ1 go to 0. So the hyperbolic Ericksen-Leslie converges to the parabolic one. So our goal is to justify rigorously this limiting process. So the main difficulty of this process is one is a changing type of equation from hyperbolic to parabolic, and the two is coupled with Navier-Stokes. So we first, before we treat this as a general case, we treated some special case. First, the case is U is just given. Another one is with Zarnescu is we completely forget about the U. We just reduce the problem to a scaling limit from wind map to heat flow in S2. So very recently we did for the general case. Here, so now look at the first case. We forget about U. So the hyperbolic system. This is the hyperbolic system, D to S2. So with damping here. So this system is a wind map from R3 to the S2 with a little bit damping here, DDTD. So one way of interpretation this system as follows. Look at the Z1 equals 0. This is the standard wind map, which can be characterized as variationally as the critical point of the function. This functional. This is the D. Now the heat flow is well known that this is heat flow to S2. This form. The corresponding this is the harmonic map. Is the right hand side equal to 0. It's the critical point of energy. This one. So relation between the harmonic map, this damping, this wave map, damping wave map, and the harmonic map is what? If we rescale this D by here T over epsilon x over the square epsilon, this D epsilon is satisfied the scaled wave map. This which is nothing but in our Ericksen-Leslie system without a U. Okay. So it's easy to say, so if we set epsilon equals 0, so this guy will go to what? Go to a heat flow. So the question is how to justify it. Now, a wave map is a system of hyperbolic equation with two initial conditions, while the heat flow is just a parabolic system with only one initial condition. So usually, the solution of a heat flow does not satisfy the second initial condition. So this disparity between the initial conditions introduce a so-called initial layer in time, so appearing in the limiting process at epsilon to the 0. So we formally calculate. I will give a little bit more details later. So a formal derivation, a analysis indicates that the initial layer has this. We can explicitly write it down. This is the initial layer. So we can construct the ansatz. The ansatz is what? This is a solution to the scaled wave map. This is a D0 is a solution to the heat flow of both the target S2. And if we add an initial layer which could be explicitly write down, and we can write this remainder term with order square epsilon. So we can rigorously justify around this heat flow and with this heat initial layer, and we can find the difference between the heat flow and the wave map is this is error term, and and we can show that the remainder term satisfies this uniform bound. Let's remark this convergence rate, I mean square of epsilon, is optimal in the sense that even for the 1D from damped wave equation to heat flow heat equation, so this the square of epsilon is the optimal rate. Now, let's go back to our original equation. I mean, Ericksen-Leslie system. Now we will treat the general case. This is a general inertial Ericksen-Leslie. Here I just use different notation. Here du this is nothing but the material derivative. D double is the second derivative. This one, this is gamma, and this is sigma. Sorry, it's labeled as a sigma tilde before. Here, this one is a mu1 to mu6, except mu4. Mu4 is here, and with initial data here. Our goal is to prove when epsilon go to 0, so this the u epsilon and the d epsilon will goes to u and d. Our goal is here. Formally, when epsilon go to 0, I mean initial density go to 0, so we'll go to u and d, and u and the hyperbolic nuclear crystal system converges to the parabolic one, which is this. Okay, this is the famous, I mean, parabolic nuclear crystal one, the Ericksen-Leslie system with the Lagrange multiplier and with the initial data. Again, because of this disparity between the initial data, so an initial layer is needed. So we get these answers. Okay, U0 is like this, and then UD here. Because of the initial data, so we guess this we try to formally derive what the initial data looks like, initial layer looks like, and we can calculate. Okay, and define this rescale the time, and finally we derive. We can find this initial layer. We can solve it. Okay, like this form. So that means this beta must be 1. Okay. So anyway, so this is our initial layer. We can calculate. So now our theorem is this. When lambda 1 equal to less than 0. And satisfy some coefficient, satisfy the condition which makes the system dissipative. So that means that there exists a small number, so that when initial data is small enough, and the system, I mean the original hyperbolic system, has a unique solution with this form. What's the form? Here, U0 and D0 is the solution, global in time solution of a parabolic Ericksen-Leslie system. And here is a UR and the DR with order square of epsilon is a so-called remainder. That's a decay rate is a square of epsilon here. And here epsilon DI here, this is initial data, initial layer, which can be calculated explicitly here. Yeah. So this is our result. Of course, the key result is to write down the UR and the DR the equation and prove the existence of the UR and the DR uniform in epsilon. When epsilon is small enough.
Good. Sorry, can I just?
Okay.
Can you just remind me in 37? What is the D tilde? That one there.
Oh,
remind me what that is.
Sorry. D tilde is the initial data of DDT.
Okay, so the requirement on the small initial conditions is not much fluid flow, small time derivative for these spin-like variables,
yes,
and weak gradients,
yes,
all have to be less than
yes, yes. That's a smallness.
No, I understand. I'm just trying to figure out what you meant by small initial data.
Yeah, it's small initial data. In fact, in some senses, a small initial data result is to say that stability of the constant solution.
Yes.
Yes. Okay, stability of this trivial solution. Okay. By the way, let me remark this epsilon. This say 0 is small enough so that okay, this guy also has a global existence. So the key is that you see. So that's the ansatz. U0 D0 solution of a parabolic one. And we want to construct the special solution of the original hyperbolic Ericksen-Leslie system of this form with a initial layer character. And the key is here, square of epsilon here is also, we can prove it's the convergence rate. I mean, the difference between parabolic and hyperbolic, the convergence rate is a square of epsilon. This is optimal. Okay? And so the UR, DR, so you can imagine, okay, go back to the plug into the original equation. So this remainder UR and the DR satisfy a very complicated form, okay, and with constraint and with initial data, and we want to prove this UR and the DR has a global in time solution when initial data is small. Now, and in fact, we prove that the key of this work is to prove the existence of the system UR and DR. First of all, it satisfies the uniform bound. Okay, so this uniform bound give us you can say square root of epsilon is less than bounding. So you can also give us the convergence rate of UR and the DR using the square root of epsilon. Okay, now the question is how to prove this. Okay, so this is the most technical part of this work. We have to what? We have to design a very subtle norm to close this energy one. Now note here is analytically the hardest part is this one. You see, this part is DDT UR. DDT UR, you know, the same order of a gradient Laplace UR. So which is the highest order. So there's no way to control it. So yeah, I have 5 minutes. Okay, so we trust me. Okay, so we very carefully designed this energy function and the dissipative rate function. Looks complicated, but okay, trust me, that's a game. Okay. And we can show that when epsilon less enough, the convergence rate we construct is equivalent to this looks much better energy node, and the energy dissipation rate looks like this. Okay, and what's this? This and this is the norm we want to justify. Okay. Now eventually we want to prove that when epsilon is small enough, and this norm is equivalent. I mean, equivalent means that exists at C1 and C2, so that this is bigger than C1 times n and less than C2 times n. Okay, and but for this epsilon and for this E and D, we could have a very good energy estimate. Okay, then close energy and take epsilon go to 0, so we can get this is a part. Okay, so in the last page, so what's next? The future work and the open problems. So first, we only consider the domain, either the whole space or the periodic domain. So the domains with the boundaries, so we haven't touched because you know and also global time weak solution. The main difficulty coming from the geometrical constraint d equal to 1. Okay, so for this case, our regularity is not enough to justify the limit. And as I mentioned, the 2D case lambda equal to 1 is okay. And inertial limit for lambda 1 equal to 0 still ongoing because we just proved that lambda 1 less than 0. And the original problem of Ericksen for the twisted solutions, nuclear ones still open, and I plan with Zarnescu, and in this program we joint work on this, try to find a class of a global time twistable solution. And how about the Q tensor error? Chance model is a start. And very recently, so you know, there is some more and more interesting on the so-called active liquid crystal one. So both for Ericksen-Leslie and the Q tensor model, and then you know the recent work, Hui-Chang Chen and Majunda and the Huang and Zhao, and they did some work for the parabolic Q tensor, for active nematic liquid crystal. So how about for this active liquid crystal with inertia one? So it's interesting, so we try to work on in future. So I stop here.
questions or comments?
You gave a quote from Frank Leslie's paper that this might be important, conceivably, even if one term to include, but do we know experimentally whether it is an important term to include?
Sorry.
Do we know whether it is important to include this extra term experimentally?
Oh, you mean this experimentally? You mean this initial?
Yes.
And to me, okay. So okay. To be honest, I don't know for which case is experimentally important for this. I just okay. So and you know, the Ericksen-Leslie itself, he mentioned that for some case, for most cases, experimentally, so rho 1 is very small, so they just neglect it. But they said for some special case, I mean, so when the anisotropic is subject to large acceleration, for this case, this rho 1 does play a role.
Well, he says could conceivably play. And I'm sure that's a little bit
I mean,
different from
sorry.
saying it does play a role.
Okay. Yeah, I know. Yeah, so, but from the point of view, mathematically, it's because it's a related to the wave map equation. So we are interested. So, but if you ask me how important physically, to be honest, I don't know.
You see, like, there is one thing I find a little bit contradictory at odds, because you take into account, this term, which, I mean, it's very good work, no doubt about that. But then on the other hand, you make a hypothesis with that viscosity coefficient, that what it does is to encourage motion rather than slowing it down. So I find it a little bit hard to reconcile, right? So you go and capture a very fine effect, but on the other hand, you keep, kind of defeating the viscosity that causes the rotation. That's so this is, I think, a real problem in some of these models.
So so we try to minimize assumption on the coefficient. So here is basically our assumption on the coefficient is just make the system distributive.
But that's a sufficient condition. It's not a necessary condition.
I agree.
Is there another question or comment?
I know the physical importance of this is questionable. Okay, I know this.
Thank you very much again for your presentation. So, 5 minutes break or not?